Okay, so today is the last lecture, and I have a very ambitious plan, but so I don't know how much I can cover. So before just going there, let me just recap briefly what I said yesterday, and so let me just take 10 minutes. So yesterday, what we considered is that we considered a sequence of IID random variables. Let me just call this variable xi1, xi2, xi(n). Yesterday I was calling them x, but I have just made a change of variable to xi. And these are IID random variable, each drawn from a distribution P of xi. So it's from the same distribution, which I assume to be continuous. So P of xi is continuous. Okay. So what I have shown is that if I look at the joint distribution of having m records with their ages, so that's basically the up to what time step they survive, calling L1, L2, Lm for a given n, that becomes completely independent of this distribution P of xi. So if you remember that initially we had this joint distribution where we wrote down this one and also the record values, right? So that depend on this distribution P. Then we have integrated out these record values, and during the integration we made a change of variable. We define something called u, which is integral of this P, and then that expression become completely independent of this P. So I think the record statistics is completely independent. So it's a universal distribution, joint distribution, independent of this P of xi. So it's a very powerful statement, right? So it doesn't matter from what distribution you pick up your random variables. So what you got finally is that L1, L1 plus L2, and so on, L1 plus L2, Lm. But then there's this constraint saying that it's n, right? We have also computed the distribution of the number of records by summing over all possible values of L's. And what we have got is again something okay. And I've said that this is the unsigned starting number, and it appears in the random permutation problem. So what we showed is that the distribution of number of records for a given n is same as the distribution of number of distinct cycles in the random permutation problem, right? And what we have also shown is, I have told at least that this goes to a form m minus log n whole square by 2 log n. So it's Gaussian about log n of a fluctuation about also log n, right? So this is what I have done yesterday. Okay. So I forgot to emphasize the fact that this distribution is completely independent of the distribution from which you are choosing your initial variables from. Okay? So this is the case of completely independent distributions. So now what we are going to do, we are going to put correlations. Okay? So as I have shown in one of the earlier classes, that one of the easiest method to build correlation is basically taking a uncorrelated sequence and you construct another sequence. So let's just put correlations. Correlated variables. So now I make up a sequence which is drawn from this distribution. These are the random variables drawn from this P of xi, which is now continuous as well as symmetric. See, in this case, it was only continuous was enough. So now I'll assume that, okay, let's just put it. So first guy, let's call it this one itself. Second guy, I add these two. Third guy, I add 3 of them. And so on. And last guy, okay. These individual guys are drawn from some distribution which is continuous and symmetric. So as you have seen before, this object, so this is, let me call it x1, this call it x2, these are random variables, this is call it x3, and this is called me xn, right? See, these x's are nothing but the position of a random walk, right? I can generate this sequence from there. Okay, so in this case, I have taken x0 to be 0, but I can also take any x0, any x0. So in fact, then I'll have a sequence including this x0, so that's the initial position, then x1, x2, and xn, right? And I want to understand the record statistics of this sequence, okay? So this is basically record statistics of this random walk for when the jump distribution, this one, is drawn from a continuous and symmetric distribution. That's the only thing. It can be anything. It can have a finite variance. It can have an infinite variance, okay? So this is the work done by Satya Majumdar and Zif, and this is the reference, okay? So you can again write down, you remember that yesterday when we derived this formula, before that we also had this joint distribution including the record values, and we have written down a joint probability distribution for the full thing, right? It involves some this thing, a piecewise thing, and then there's a big delta function, right? So you can again do it that way. So here I am not going to do it that way because so you can actually look at that method in that article, and I'm going to come back to the same method here in the second one. So I'm going to use a different method just because it's a school, and one of the objectives of this school is to learn different methods, right? So I'm just going to just give you a different method. And what I'm going to do, I'm just only going to concentrate on these objects, okay? And not the full distribution. And also, I'm just going to define M in a slightly different way. So in this case, M is the number of records, right? Which also includes the first record, that's first value, that's by definition you call it a record. So in this case, so I'm just going to call it now, so let me just put a record is of random walks, and the observable I am going to concentrate on this is M, and M I am going to define is the number of record breaking events up to steps, right? So basically, this is the observable which anytime a new record is created, this picks up. So this number of records is basically M plus 1, right? Because by definition, the first observable you just call it a record, right? So this is related to record, is just divided by 1. Okay, is it clear? So this is basically number of record breaking events. It's not the record itself, Okay? So it just differs by 1 because by convention, where the first observable, we just call it a record. Okay? So now, what I am going to teach you is something called this, it's like when you have a continuous variable, you write down something called differential equation. So here you have a similar equation, right? So let me define now P of Mn is the probability of having M record breaking events up to n steps, right? So let me draw a picture of the random walk. Let's say something like that. So you have these steps. The steps. This is step 1, step 2, and let's say this is step n, right? These are the steps. Since I'm just going to look at the number of record-breaking events, the first position doesn't matter actually where x0 is. So it starts from somewhere here. Okay. So what is a record-breaking event? So record-breaking event is a 1 if the random walk next time exceeds this value, right? So this guy stays there. It only moves, jumps at the tick of this clocks. It moves there, and then suppose it goes there. So that's not a record-breaking event, right? And then it goes up to there, and then it jumps by something. The jump length are not same, need not be same. So these are actually not same. These are drawn from this distribution P of xi, right? These are the jump length. So next time, suppose it just goes somewhere there. Okay. Now in the third trick, suppose it goes somewhere here. Okay. Then it goes there. Suppose it jumps somewhere there. So that's a record-breaking event, right? Because it's the first time it exceeds the previous value. And then again, okay, it can go there, it can go something like that, it can go there, it jumps somewhere there. So that's a record-breaking event. It goes there, 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 there's something like that, something like that. So that's a record-breaking event, okay? And then it keeps on going to that, and at some point, let's say this is the guy, it releases here, and let's say that's the last record-breaking event. That's what we are calling it. So this is the first record-breaking event, this is the second record-breaking event, and this is the mth record-breaking event, okay? And then there is, of course, no record-breaking event after that. Okay, okay, this is somewhere here, okay? And then, of course, it goes there, something like that. Okay. So therefore, if I want to write down a equation for this, P of M sub n for m greater than 0, okay, for m greater than 0, E of, so m is integers 1, 2, 3, 4. I'm excluding 0 part. So this is equal to. So this is says that during these n steps, it has m record-breaking events. Okay. So then it says that every record-breaking event is a first passage event. Basically, this is the first time it crosses that one. So let's say first record-breaking event happened in n steps. Okay, so this happens in n steps. So this is equal to probability that it crosses this origin for the first time in the nth step. Okay, times if it crosses the origin, it has made one record, right? Because that's a record. So I have to find that there are m minus 1 records now, because already one record is made, in time step n minus n. Right? These are the rest of the time steps. So this is your time step, which is n minus n steps. Okay? But this n can happen in anywhere. So what is the minimum value of n can have? It could have gone up at the first step itself, right? N equal to 1. Can you make the first record at the nth step? So that is n plus 1 minus n, m. Okay, is it clear? Okay, just you can check. Suppose m equal to 1. The case m equal to 1. What is the probability of making just one record? That could have been made at any places, right? Because it can be the first step, second step, so then it would have gone from 1 to n. What about n equal to 2? M equal to 2 records. 2 records cannot be made at this last one, right? First record. So at least it has to, one has to made it here and then the next one, and so on, right? So this is the equation you have to solve, where m is between 1 and n. Okay? So I have to also tell you about m0, right? Because you can also have m equal to 0. That's the probability of not making any records up to that time, right? Basically the worker just stays down, then he doesn't make any record, okay? So this is the equation we have to solve. Yeah, just 1 minute. See this one, these individual steps are independent, right? So whatever happens here, jump, the next jump doesn't depend on previous jumps, right? So this is something called Markov process, right? So whatever happens here, it doesn't. So therefore, it says that what is the probability that there are m records? There is a probability of making one record at the first record at the nth step. So that's the probability of making the first record at the nth step, times the probability of making m minus 1 records in the n minus 1 steps. So this factorizes, right? Yeah.
So that one is just like P of 1 slash small m.
No. It just says that what is the probability that it makes first record? It says that the worker stays below all the way up to the n minus 1 and the nth step it jumps basically, right? Okay. So let me define now this probability. What is f of n? So f of n is the probability that the random walk starting at the origin. So this can be anywhere because it's, again, the random walk is translationally invariant in space, right? So any place, so from here, you can see that it's basically, okay, it has to cross the previous starting value, right? So that starting value, we can therefore just call it origin, or starting at some point, or some guy x0, crosses or exceeds, basically crosses from below, crosses the origin or x0 for the first time at nth step. Okay, so this is usually known as the first passage probability. And f of n is the first passage probability. Okay. So let me define another variable. So what is f of n? So f of n is basically the probability that, what is the first step? First step is this one, okay? So probability that less than 0. Second step is also, at the second step also it's less than 0. Less than 0. At n minus 1 step, this is less than 0. Then you have all these sums. For third step, zeta 1, zeta 2, zeta 3, or xi 1, xi 2, xi 3, and it goes on up to I1 plus n minus 1 less than 0. So it stays below till n minus 1 step. And then at the nth steps, it crosses. So is greater than 0. This is its probability. So let me define another probability. Let's call it Qn. Probability that this is less than 0, and so on. Less than 0, and is also less than 0, right? So this also less than 0. So the second one says basically that the probability that the Walker, so this is the probability that the random walk doesn't cross origin, doesn't cross from below till n steps, so it can cross after n steps. Okay, so then what is p of 0n? So you can immediately see that what is p of 0n? Probability of making 0 records in n time. So q of capital N is just a probability that it doesn't cross up to n step. Yeah, thanks. Okay? Yeah. So now we have to solve this equation. Okay? So when you solve this equation, so the solution of that equation gives you the probability. So we'll solve this equation, and let's make a change of variable. Let's call m equal to n minus n. Okay, just a change of variable. So then, what is the right hand side? So let's call it, okay, this is left hand side, this is the right hand side, the whole thing. So what is the right hand side? So like what I've, okay, let's put it here. M equal to n minus n. So right hand side becomes what? So now I'm writing in terms of m. M is my now variable. So n is replaced by, or n is n minus m. So this is n minus m. P of m minus 1, n minus n is m. Okay, so this is what you have, And where does m run from? So when n equal to 1, m equal to n minus 1, right? So let me just put it here. And when n equal to this guy, m equal to m minus 1. You can just check, right? So these are the limits. So it's the same one I have just written down in a different way. Okay? So whenever you have something like that sum, the trick is to, okay, it looks very complicated. One of the trick is to just make it all the way from 0 to infinity, and these conditions put it here as some theta functions. Right? I think similar thing we did for these integrals. Right? So let me just put it, this m runs from 0 to infinity, and let's call it f of n minus m, p of m minus 1, m. Okay? But now, what is the minimum value of, what is the, m is bounded by n minus 1. So let me call it theta of n minus 1 minus m. So these are discrete theta functions. Basically theta 0 is also 1. It's basically whenever it's greater than equal to 0, it's 1. Okay? So this corresponds to that condition. I still have to write down this condition. And this condition says that theta of m minus m minus 1, so this plus 1. Right? So this is same as the previous thing. So okay, let me just call a theta of square bracket this thing, and let me just define the theta of square bracket k is equal to 1 for k greater than equal to 0 and 0 for k less than 0. The k is integer. Okay, so this is how I define. Okay, so therefore this equation now I can just write it using this guy, and that equation becomes, so p of m n is n equal to 0, m equal to 0 to infinity, small m, f of n minus m, p of m minus 1 m, then theta of n minus 1 minus m, and theta of m minus m plus 1. So can you guess the reason why we have put it in that form? It's, in fact, it's the same. You could have actually done with the previous one also, right? But okay. Okay, so this is what we have, where m is, this is valid for m between, so here 1, m, n. And for 0, we have this thing separately. Okay? So now, we can define, so whenever you have this kind of equations, one of the easiest way to solve is defining generating function, right? So we define these generating functions, which is called f of z for your corresponding to this guy. So let's define as fn z to the power n equal to 1 to infinity, okay? Because this guy is the first basis, right? It only takes from only up from step 1 happens, right? Okay, this is what we define. Then q of z is qn z to the power n. Here n can go from 0 to infinity. It's asking what is the probability that it survives up to n steps. It says that, okay, what is the probability that it survives 0 step? It's just 1, right? Because it just started there. Okay. Then you can also define this probability generating function. Now it's double generating function zw, which is n goes from 0 to infinity. Let me just look at this. Z to the power n. M goes from 0 to infinity. And W to the power m. P of Fn. But of course, when we have defined this object P of Mn, there's also this restriction, right? M is less than equal to n, right? Because m cannot be more than n. So theta of n minus m. Okay, this is what you have. Okay, so now you can, this one we are going to take away the n equal to 0 part and then the other part. So this one is n equal to 0 to infinity. Okay. Z to the power n. So this one we have basically we are going to write take away the m equal to 0 part and the rest of this thing. So then m equal to 0, so that's w. So I'm just going to write m equal to 1 to infinity, this guy. Okay. Yeah, sorry. Okay, so n equal to 0 part, when n equal to 0, okay, what is the value of m? Only 0 is the possible value. So P of 0 n. This is the m equal to 0 part. I am keeping this thing. This is the 0th part. No, sorry. So what I am doing is, this term I am just taking the m equal to 0 part and the rest. Then plus z to the power n. Let's look at w to the power m. So this is m equal to 1 to infinity. Okay, I'll just put the thing. This is over n. P of m sub n theta of n minus m. This n goes from 0 to infinity, right? Because I have only taken this m equal to 1 part here, so but n I have this there. But for n equal to 0, m cannot be positive, right? Because m is a number of records, so therefore this n is also goes from 1 to infinity, right? All those terms where n equal to 0, m is greater than 0, they are just 0, right? So this is what I have. Okay, so therefore I can now put this generating functions here. This guy is nothing but q of n, right? This is what we found. Okay, so therefore this is equal to q of z plus this guy, and that guy is, let me just write down now, n equal to 1 to infinity z to the power n, m equal to 1 to infinity w to the power m, theta of n minus m, and this guy we have written down here. Right? So I'm just going to substitute that guy, and that says, because here m is greater than 1, right? Greater than equal to 1. So I'm going to substitute m equal to 0 to infinity f of n minus m, p of m minus 1 m, and then I have this theta function n minus 1 minus m, and theta of m minus m plus 1. Okay? Okay, so now you can look at this guy. keep it there and we'll just go up. Okay, so now call n prime. Okay, so you just change n to n prime minus n prime plus m plus 1 and m equal to m plus 1. Okay, you're just changing this thing. Then what you have, because now these are just dummy variables, right? You're just summing over all these things. Okay, so what you have is a g of zw. This is equal to. So you have a sum over m that I take it outside 0 to infinity. Okay, then okay, I have a sum over n prime and I have a sum over m prime. Okay, so all these limits will put it. Okay, so what you have is z to the power n. Z to the power n is n prime plus m plus 1. W to the power m is m prime plus 1. Okay, and then you have these theta functions, theta of first guy n minus m. So what it becomes? It becomes n primes plus m minus m prime, right? This basically this 1 cancels. Okay, and then you have that this theta function. That theta function is second one, which is this n minus m minus 1, n minus m minus 1, that's n prime, right? So n prime, and then you have this theta function last one, n minus m minus 1, and that is m minus m prime. Okay, so this is what you have, right? This one you just put m equal to m plus 1. What did I do? M minus, yeah, this m minus 1 just becomes m prime, right? So this is what we have. And what are the limits? These limits, of course, okay, infinity when it's, this is over n prime, when n prime infinity, it's still infinity. And what is the value of n prime when n is 0? This is just n is 1, so this is just minus m. This one, okay, 1 minute. This one, this is only for the rest of the guys, so there's still q of z there, right? So let me just put q of z on the left hand side. Okay, yeah. And now you see that there's this theta function that makes, it says that it has to be greater than 0. So therefore this limit actually goes from 0 to infinity, right? So this changes because of the theta function. This becomes n prime equal to 0 to infinity because of this theta of n prime. Okay, and what about the limit of m prime? M goes from 1 to infinity, therefore m prime goes from 0 to infinity. Right? So therefore all the three limits basically goes from 0 to infinity. Okay, so now let me just write it down. This guy is basically, it's still there. Yeah. It's still there. Yeah. So now let me just write down n prime equal to 0 to infinity z to the power n prime plus 1. Okay, so I have to write down these guys, right? These guys I have not written down. What happened to f? These all guys are there. What happened to f? N minus m, that becomes n prime plus 1. And what about p? What about p? M minus 1, that becomes m prime. So m prime given n prime, right? No, m prime given m, right? So it has everything, okay? So now you see that what are the places you have n prime, you just take it out, okay? So when you take it out, that thing makes you from 0 to infinity, z for n prime plus 1, f of n prime plus 1. Is there any other places where you have n prime? Nothing, right? So I have taken out all the n prime. So this is basically all the n primes are out. Then how many w's are there? M plus m prime plus 1. So let's keep one w here. And then I have this guy. There is sum over m, which goes from 0 to infinity, and z to the power m, that's basically coming from there, z power m, that is left over. Then m prime goes from 0 to infinity, that's still there, and then z to the power m prime, p of m prime m, and theta of m minus m prime. Right? What about this guy? What about this theta function? This theta function was taken care here. This theta function is here. What about that theta function? N prime goes from 0 to infinity, right? M goes from 0 to infinity, and m prime is less than m, so therefore this is always positive. It just becomes theta of 1, right? So therefore this guy is always positive, so therefore it's redundant. So we don't need the theta function, okay? So this is what you have. Now this one you already have seen. This is nothing but this generating function, because it's 1 to infinity, but since this is 1, I can now define n plus 1 as like little n, then this generating function is actually exactly same as this generating function. Right? What about this guy? This generating function is exactly same as this generating function. You have two variables, one variable to the power this thing, so let your small m is like your capital N there, because these are dummy variables. That other variable, and then p of m slash n, p of m this thing, w to the power m, w to the power m prime, and then this theta function there. Right? So this is this generating function. So this guy is your f of z, and this guy is your g of zw. Okay? So therefore you have a equation which is z of zw minus Okay, so this is equal to Q of Z plus F of Z W G of Z W. All right. So what is the solution? G of Z W 1 minus W F of W is equal to Q of Z. So therefore, G of Z W is equal to QZ by 1 minus W F of W. Okay? F of Z. Yeah. Okay. This. So you could have actually derived this equation by just doing this, writing down this factorized way, okay? But I've just done in a different way so that, okay, you just learn that you can, the same thing can be derived many different ways, okay? So this one, now you can also see that this is equal to Q of Z, and then this guys is like something like 1 over 1 minus X, right? So therefore it has a simple power series expansion, and that power series expansion is m equal to 0 to infinity W to the power m z to the power. All right, so this is like 1 over 1 minus x expansion. Okay, so therefore, if you look at the so if you look at the, now what is this g of this thing? That's defined somewhere here. That's the double generating function. Now look at the coefficients of w to the power m, and if you look at the coefficients of w to the power n, then that's the generating function with respect to n. So n goes from 0 to infinity, z to the power n, p of m n. This is given by this guy, q of z, then this guy, fz to the power m. So this should actually go from m to infinity, because you will see that because all the other probabilities are anyway 0, right? But okay, I can just for the time being write from 0 to infinity. Okay, for all the other probabilities where m is greater than m, that will come out to be 0 anyway. Okay, okay. So now you see that basically to invert the generating function, we need this guy and that guy, right? These things we have not found here, right? And what is this one? This one is the generating function for this survival probability, and that other one is just the generating function for the first spaces time probability. Okay, so now, so there is a very strong theorem. It says that which says that Q n for any continuous and symmetric distribution, so it doesn't matter which distribution is this is universal, and that's given by 2n choose n 1 over 2 to the power 2n. Okay, so it means that, okay, if you just look at the generating function, this is a simple generating function to compute, right? So, and this generating function is basically given by 1 over 1 minus z. So this is completely universal independent of the jump distribution as long as the distribution is continuous and symmetric. Okay, so this is the probability that starting with the origin, it doesn't cross the origin up to step n. Okay, so that probability is completely universal. Okay.
One.
Huh? Yeah. It's there. It should be. It should come out. It's there actually. So this should go from m to infinity. It's there. So it should come out of the final expression actually. It's there. This expression, the theta function, it's still there. So you can actually put that theta function. And what does the theta function say? This theta function says that n should go from m to infinity. Right? Right? That's what the theta function says. It says that n is greater than or equal to m. Yeah? So it just says that the lower limit is from m to infinity. Okay, I can just put it. Okay? Yeah. It says that for any continuous and symmetric jump distributions, if you start with some point, let's say origin, what is the probability that the random walk doesn't cross the origin up to step n? Okay? And that probability is universal and it's given by this one. Okay? And what is Qn? Qn is also the probability that it doesn't cross the origin up to step n, so therefore it crosses the origin only after n, right? So this will be equal to Fk, where k goes from n plus 1 to infinity, right? So this is same as the probability that it just crosses the origin after some step, or in other words, it says that f of n is equal to q of n minus 1 minus q of n. Okay? Now you have the generating function for q. You can also find out the generating function for f from here. And what you will find is the generating function of f is given by 1 minus z. These are check. Given this, check this one. Okay? Check also the normalization, everything. So now, putting everything together, so what we have is here is that, let me write down 1 minus z, and then 1 minus square root of 1 minus z to the power m. Okay? So this is what you have. Okay. So you need to invert this. Okay? So I'm not going to invert. So maybe that's an exercise. Invert this. And then what you find is that P of Mn is given by 2n minus m, choose m, 1 over 2 to the power 2n minus m, this is 4, okay. So you have a universal relation for the number of records in a given, number of record breaking events in a given time n, okay. How do you invert? So that's an exercise. Basically, you know that formally it's given by, what is the inversion formula? Given this, what is the inversion? What is this? 1 by 2 pi I dz, z to the power n plus 1, and then this term, right? So which is 1 minus square root of 1 minus z to the power m by 1 minus z, right? So you have to do this. You can also expand in powers of m, and then you just expand this and just basically find out the coefficient of z to w to the power m. But you can also do this integral, and this integral has some branch points at z equal to 1. So you carry out those integrals and you'll find this formula basically. Okay, so let me just quickly say something. Okay, that's also homework. Let me just give you some more homework. Since today is the last day, you don't have to come and show it to me, but you just do the homework. Given this formula, also compute the m, and you show that for large m, this goes like 2 pi square root of n. So it goes like square root of n. Do you remember how the record number grows for the IID random variables? Log n. So this as opposed to log n, right, for IID. Just log n. Variance, also compute, and show that variance is again some 1 over 1 minus 2 by pi n. So variance goes like n, and their variance was, for IID case, it was again log n, right? Okay. So you can also Pmn for large m and n. So these are, you can write down in terms of factorials, and you can do this Starling approximation, right? Show that this goes like 1 over square root of n times some scaling function of m by square root of n, because that it goes like square root of n, where the scaling function is given by 1 over square root of pi e to the power minus x squared by 4. Okay? Yeah, x is greater than equal to 0, right? Because this the number is a record number, it's a positive value, so you can just show this. Okay? So this is the record for random walks, and you see that already you get very different results from that of IID random variables, right? So what is the peculiarity of random walk as compared to IID random variables? The IID random variables is a stationary time series, right? Like if you look at the variance, it doesn't grow, right? But the random walk variance grows. Right? So that's why there the variance doesn't grow, so it's like a stationary time series. So therefore it becomes harder and harder to make records. The record number grows only logarithmically with n. Okay? But here, random walk, the fluctuation grows like square root of n. Right? If you have studied this random walk, the fluctuation itself, so therefore the fluctuation grows. So when the fluctuation grows, you can also make more records. Right? So this can be a good model, therefore, in system where there's some external drive or something because of which your system is getting, the variance is becoming more and more, okay? So I'm not saying that this is a model for global warming, but it's basically some systems where you see that the fluctuation grows with time, basically. So there's something and something, right? So this can be some good first step model for those kind of systems, okay? Yeah. For example, this can be a model for finance. Like a finance, usually random walk is quite a good model for finance. And so it's usually given by some logarithmic of random walk. But since this log is a monotonic function, whenever you have a record in log variable, you will also have a record in this variable, right? So if you ask what is the record statistics of a log of a random walk, is same as the record statistics of a random walk, basically. Okay, so now the next part, what I'm going to do, so this random walk, I have assumed that, okay, you have a clock, and let's say every 1 second this clock ticks, and then you basically make a jump, okay? There are many systems where, of course, things do not change uniformly in time. And for those kind of systems, there's this model called continuous time random walk. So basically at each point, you wait for some time, and after waiting time, you make a jump. And then again, you wait for some time, and again you make a jump. And this time you wait at a particular point, you just draw from some distribution. Okay? So therefore, so in some sense, that random walk model is the model where you have a continuous time random walk, and waiting time distribution is just a delta function at a time equal to 1. So every 1 second or whatever minute you just make a jump. But here you just draw it from a distribution. Okay? So you again have this time series. This is now in continuous time, x1, xt1, xt2. So t0, you just call it 0. You have this time series, and now you are not looking at the number of jumps, but you are basically considering, if I just look for, let's say, 1 hour, how many records are there? Okay, so let me just make a diagram. So this is your t. So this is your observation time t. At some time you just fixed it, and you have started from some point here. So let's call it by, as I say, by convention, the first point we just call it a record, and then you go for some time, you just wait there, you don't do anything, okay? And then you make a jump. And this jump, again, you draw from this distribution P of xi, which is again continuous and symmetric, okay? And then after that you make a jump. Since you have gone up, now this is a record. This, call it R2. And then you go there, and then you go somewhere there. That's not a record. You go something, you go there, go, maybe you wait for a long time, you go there, that's a record, right? Because you have gone up, that's a record, R3. And maybe you go somewhere there and immediately make a jump, go somewhere there, okay, maybe jump there, go somewhere there, something like that, right? So in this realization, there are only 3 records, 1, 2, 3, right? Because after that you have not made any record, and this is your final observation time, okay? So this time, let's call it tau 1, this call it tau 2, this call it tau 3, and so on. So these are drawn from some distribution. This is a one-sided distribution because it's a time. So it's drawn from some distribution, P of tau. Okay? Yeah. And now M is equal to my number of records. I have again come back to number of records as opposed to the record breaking events, right? M is my number of records, and these ones, as we have said before, these are, we are calling it ages, the time between successive records is L2. These are my ages, okay? So the record survived for this time, but these are now L1, L2, these are now continuous variables, right? Because this is actual time. So at time at which it makes this record. Okay, so therefore let me just define this joint distribution, again P of M, the probability of having M records with their ages, these are the times till which they survive, L1, L2, Lm. This last bit is my Lm. And you see that the last bit is a bit different. These previous bits, after that time, there's a new record generated, right? But this last term is basically at which does the observation stop. So that at Lm, after waiting for Lm, the next record is not generated. Next record is probably generated, okay, I don't know, it might generate somewhere later, okay, after Lm. So the last definition of the last age is different, but it's basically, okay, till that observation time, that's the time you have survived. right? And then observation stops. Okay, this and given t. Okay, so this is my joint distribution. Okay, so joint distribution of having m records with L1, L2, these are the ages, and the observation time t. Okay, so this one I can now write down this thing. So what, as I said, that this is a first species event, record is a first species event. So what is the probability of having this L1? It says that probability that there is a first species event here, right? So this is same as f of L1. So this is now f of L1 dL1 is a probability. This is now in continuous time. So there this Fn is the probability itself because it's happening in the discrete time, right? So this is a probability density f of L1. And then again starting from this up to time L2 it again crosses. So this f of L2 is the first species probability density. It goes on till the m minus 1th guy f of L of m minus 1th guy. As I said, the last guy is bit different. What is the last? Last guy says that starting with some point, what is the probability that it doesn't cross up to that time? So for the amount of time Lm, it doesn't cross. So that's a survival probability, right? So in this cases, it was crossing probability. Okay, this is the first species probability. The last guy is the survival probability. Okay, so this is Q of Lm. Okay, and then there is this usual delta function which says that if I just add all these times, it should be equal to my observation time t. Right? So therefore, this delta function which says that L1 plus L2 plus m minus t. Okay? So if it was, so I still have to find out this f's. Okay? So if it was the random walk case, the one I have described, okay, this would have been f of n1, f of n2, right? The same f I have defined here, but these f's are slightly different. Okay? So I could have started the random walk problem, I could have started with this one. That's the way you can actually look at the paper, right? And I could have derived the same formula I have derived today, okay? So that method was to just give you a different method, basically teach you a different method, okay? So this is what I have. Now I have to find out what is f of L1. So what is f of L1? So f of L1, let's say f of L. So I have to find out this object, right? So what is this object? Let's look at a diagram. It says that, okay, I start with some this thing, and at time L, between time L and L plus dl, I cross this one, right? So before that, what is happening? So this guy is probably going there, and then it's something like that, it's going from something like that, it's just staying below. And then it's crossing here, right? So this is now like my one individual cell, okay? These times I have drawn from, this is tau 1, this is tau 2, this is tau 3, and so on. So these are the times I have drawn from this distribution P of tau, right? So therefore, f of L is, there are n jumps, suppose this n can be anything, and these changes are happening only during the jumps, right? The probability that it crosses at the nth jump, okay? But this number of n can be anything from 1 to infinity, And given this, there are n jumps. What is the probability of this event, right? So this is times the probability of the first jump happening at tau 1. So what is that probability? So you have to integrate over all these variable, let's call it, this is your tau n. You have to integrate over all these variable 0 to infinity. Okay. What is the probability of finding a length tau 1? Probability density. So that's rho of tau 1. These are all product. Okay, rho of tau 1 times rho of tau 2 and all the way up to rho of tau n, right? Because at that point there is a jump happening. Okay, rho of tau n, and then again you have to find out delta because this times add up to L, right? Delta of tau 1 plus tau 2 plus tau n minus L, right? This is what you have, starting from this guy all the way up to here, right? This is the expression for this object. Okay, so whenever you have something like that, what do you do now? So look at the generating function, right? So what is the generating function for this continuous variable now, which is positive? That's just a Laplace transform, right? So then you can consider this variable as, which is 0 to infinity ds e to the power minus sl of f of L. So what does it do? So you have this guy n equal to 1 to infinity, and now you see that this is the delta function which you are keeping all these integrals together, right? You cannot do this integral. Once you carry out this integral over L, this delta function will go away and this SL will be replaced by this tau 1, tau 2s. So therefore you will have these integrals d tau 1 e to the power minus s tau 1 rho tau 1 0 to infinity 0 to infinity d tau 2 e to the power minus s tau 2 rho of tau 2 and so on. How many of them are there? 0 to infinity d tau n e to the power minus s tau n rho of tau n, right? There are n of these guys, but these guys, all of them are same. No, it's just that just the integral, but these taus are just a dummy variable. And what is this object again inside? It's just similar to that. If this was a Laplace transform of this guy, this is just a Laplace transform of this object, right? So the Laplace transform of this object you can define as rho tilde of s is 0 to infinity ds e to the power minus s tau rho tau, right? So therefore what you have is f tilde of s is equal to n equal to 1 to infinity. How many of them are there? There's this f of n that we have forgotten, right? There's this f of n, right? So there's this f of n, and then there are n of these guys. So this is rho tilde of s to the power n, right? Now this f of n is same as this f of n for the random walk case. And if you remember the generating function of this thing, what is the generating function? What is the generating function for f of n? 1 minus square root of 1 minus z. What is z now? Rho tilde of s. Okay, so this is what you have. Similarly, I can now write down the generating function for this one, right? Q of L. Okay, so what is Q of L? So Q of L is again is the similar diagram except that last bit, right? This is my L. So it says that till that time it doesn't cross this origin, right? For Q. So the Q of N what is the probability that it doesn't cross the origin up to that time steps? This is this number of jumps, right? That can be anything now. And within this number of jumps, it doesn't cross. And then we have to look at the last guy. During this number of jumps, it's not crossing. Okay. So what is the probability that it doesn't cross up to n jumps? That's this Q of N, which we have found it there. Okay. N can now grow from 0 to infinity. Okay. Probability that, so this is, let's say this is my N now. This is my tau N, and this last bit, let's call it tau of N plus 1. So this is when the nth jump is happening, right? So this one is Q of N, and then what is the probability that it's not, what is the probability of having those many jumps? Again, it's the similar object, all the way up to here, it's a similar object, it's 0 to infinity, d tau 1, rho tau 1, 0 to infinity, d tau 2, rho tau 2, and so on, and 0 to infinity, d tau n, rho tau n. So this is the probability of each these jumps, okay, and then that was the last jump happening, right? After that there is no more jump, okay. What is the probability that it doesn't jump within that time? What is the probability that for this tau of n minus 1 it doesn't jump? So that's the probability that it jumps somewhere after that, and that portion is d tau n plus 1 e to rho of tau n plus 1, and sorry, okay, d tau, this is rho tau, okay, and this one, this tau. So what is the probability that it does not jump within this time? That's the same as the probability that it jumps after tau of n plus 1, right? So this limit goes from tau of n plus 1 to infinity, right? So this is the last bit. No, this is this last bit. So this last bit is always different, right? Even there you saw that there is a last bit which is different, right? So again you can now take a Laplace transform, and what will be the Laplace transform? There is this, of course, this delta function, right? If the delta function is not there, then tau 1 plus tau 2 plus tau of n plus 1 minus, sorry, what did I say? Minus L, right? Did I write down the thing here? Here also there was this, yeah, it was already there. Okay, so now if I take a Laplace transform with respect to L, similarly as before, it will just remove this delta function, and instead of e to the power SL, it will become e to the power S tau 1, e to the power S tau 2, and so on, right? So therefore this guy will become something n equal to 0 to infinity Qn rho tilde of S. There are n of them. So this is for this guy. And then this last guy. So last guy is a bit different, right? So last guy is, what is this last guy? E to the power minus S tau of n plus 1, 0 to infinity, tau of n plus 1 to infinity, d tau rho tau, d of tau n plus 1. This is the Laplace transform of the last bit, right? So how do you evaluate the Laplace transform of the last bit? How do you evaluate the Laplace transform of the last bit? You do by parts, right? When you do by parts, you should integrate this guy and differentiate this guy. Right? So what is the first term? First term is this integral tau of n plus 1 to infinity d tau rho of tau. Differentiation of this guy, e to the power minus S tau of n plus 1 by S, 0 to infinity. That's the first one. Then minus 0 to infinity d tau of n plus 1. I have to differentiate this guy. So when you differentiate this guy, what do you get? With respect to tau n plus 1, that gives me minus rho tau n plus 1. And I have to integrate this guy. This gives me e to the power minus S tau of n plus 1 divided by minus S. Right, here it is minus S. So now you see that this guy is equal to, when it's infinity, this goes to infinity, so that's 0, also this goes to infinity, 0. When it's 0, this 0 to infinity is normalized to 1, right? So this is 1, so it's 1 over S, minus that minus, and then this minus cancels. And you see this, what is this object? That 1 over S, I take it out. And what is this object? This object is just rho tilde of S. Right? So therefore, this is 1 over S, 1 minus rho tilde of S. Right? So we have this guy, then 1 minus rho tilde of S by S, which is coming from this last part. Okay? So this is what you have. And this sum again, you can do, right? You know that sum. What is that sum? We have already done that sum. 1 by, so this guy is 1 by square root of 1 minus Z, and Z is rho tilde of S. Right? So therefore this becomes 1 minus rho tilde of S by S. Right? So therefore, if I just take a Laplace transform of this guy with respect to t, now 0 to infinity dt e to the power minus st p of m L1 L2. So what is this guy? With respect to t, that's going to take out this delta function, and it is going to put this e to the power SL1, e to the power SL2, and so on. So this will just factorize it to the Laplace transform. Okay. So how many f's are there? What is the answer? So there is 1 for Q. So this is Q tilde of S. And then there are M minus 1 for F. Right? So this is basically the similar expression you had for this, more or less similar expression you had for the random walk case, right? So now this, let's just put it, this thing. So Q of S is given by this. So square root of 1 minus rho tilde of S divided by S, and this guy is 1 minus square root of 1 minus minus 1. So this is what you have for the Laplace transform. Okay. So therefore, to find this object, we have to find the Laplace transform of this rho of S. Okay. So if I am interested in large time behavior, that comes from the small time behavior of the Laplace transform. Okay. So now there are two kinds of cases. The mean time is finite, and the other cases the mean time is infinite. Okay, there are two cases. It's like that when you discuss in the first case for this sum of random variable, there's these two cases where the variance exists and the variance is infinite. So here the mean for the Laplace transform. So if the mean is finite, so how should rho of S should behave for small s? What is the mean? Mean, if I just take a derivative, negative derivative with respect to S, and then put S equal to 0, that gives me the mean, right? Because if I just do minus del del S of rho S, so this gives me 0 to infinity ds e to the power minus s tau, that takes away the tau and rho tau, and then if I put s equal to 0, this guy becomes 1, and this is just the definition of mean. Right? So therefore, if the mean exists, the first derivative should exist. The same argument we have given for the variance, right? So if the first, at s equal to 0, it's always 1, right? That's just a normalization. This is just a normalization. S equal to 0, it's always 1. Now, if the mean exists, how should this? So this will be the so first derivative should exist, right? So therefore, this should be tau times s, right? Because if I take a first derivative and then higher order terms, because if I take a derivative now, it will give me mean tau. Okay, so therefore it has to be something like that. The lowest order is linear in tau. Okay, so let's just set this to be 1. Okay, it need not be 1. Just for simplicity, just put it 1. Okay, so the mean is 1, suppose. Okay, so therefore it just, okay, I have some form 1 minus s. If mean is infinity, how should it go? The first derivative should diverge at s equal to 0. So it should go like s to the power some alpha. 1 by s you cannot have, because at s equal to 0, this should be equal to 1. Right? So 1 minus alpha, again there can be prefactor, but I am just putting the prefactor to be 1. Okay? And alpha should be less than 1. Okay? So here also you can prefactor, you just put it to be 1. It doesn't matter, you're just scaling out this thing. Okay? So this is the behavior. So then your Yeah, I'll just take 5 minutes, maybe then I'll finish it. This Laplace transform becomes what? So you had this P of m t e to the power minus st, okay? So what I have done, in fact, so from this, okay, I should have said that from this, what I have done, I have looked at the Laplace transform of this object. 0 to infinity dt e to the power minus st p of mt, where I have also integrated over all the other variables, dl1, dl2, and dlm. Okay, I have also integrated over all the ages. I'm just only interested in the number. Okay, so therefore the whole thing you can just write it as dt 0 to infinity. So what is this? This goes like s to the power alpha by 2, because one. So now let's put both together, and we say that okay, rho of s is 1 minus s to the power alpha plus this, and alpha is less than equal to 1. If alpha equal to 1, the mean exists, and if alpha is less than 1, mean doesn't exist, right? So this is now given by s to the power alpha by 2 minus 1, right? That becomes s to the power alpha, and then 1 minus s to the power alpha by 2 m minus 1. Okay, this is what you have. Okay, now we are interested in a scaling limit where basically time is large. If I look for a large time, I'll make more record. Okay, so therefore I wanted a scaling limit, and large time is basically s is small, m is large. So what you have in that limit, it goes like alpha by 2 minus 1, and this thing becomes exponential, right? M is very large and s goes to 0. So it goes like exponential of minus s to the power alpha by 2 m. So you can forget about this m minus 1 now, right? It's just m is large anyway. Okay, so you have this scaling limit. So this scaling limit says that so this is equivalent to, it says that your P of mt also should have a scaling limit, and that scaling limit says that okay, this goes like s to the power alpha, so time is like reciprocal to s. So it says 1 over t to the power alpha by 2, some function which depends on alpha, m by t to the power alpha by 2. So it's just imagine that when alpha equal to half, it was m by square root of n for the random walk, right? It was like time was like this thing. So you should have a scaling function like that, and then you can actually put it there and show that 0 to infinity. Okay, let's take this. So you can take the scale variable t equal to m by 2 by alpha y and m 2 by alpha s, you call it lambda. With this variable, you show that e to the power minus lambda s y to the power minus alpha by 2. Just check it. G alpha of y to the power minus alpha by 2 dy. This is like a Laplace transform. This is lambda y. This is like a Laplace transform with respect to y. This is given by lambda to the power alpha by 2 minus 1 e to the power minus lambda to the power alpha by 2. Okay, this is some Laplace transform. And you have already seen a similar Laplace transform before, e to the power minus lambda to the power nu. You have seen some mu, let's call it. Okay, that was for the case where it was completely symmetric. Okay, that was a Fourier transform. But if you have again a stable distribution completely asymmetric, okay, so you can take a Laplace transform. It's a Laplace transform of a stable distribution, and that is called Levy stable distribution. Let me just write it down. E to the power minus lambda y L mu of y dy. So this is called the Levy stable distribution, one-sided. Right? It's only from 0 to infinity, and that's their Laplace transform. And then you can see that if you just take a differentiation with respect to lambda, you basically get this guy. Right? So therefore, finally, if you just combine, so what you can, let me just write down the final formula because we have to go for lunch now. And the final formula, you just put it there and then you'll find out. There's Z alpha, you just compare this, take a derivative of this Laplace transform with respect to lambda and then compare with this one. Z lambda of x is given by 1 over alpha by 2 x to the power minus 1 plus 2 over alpha L alpha by 2 x to the power minus 2 over alpha. Okay, so this is what it gives. But it's given in terms of the Levy stable function. This is that the argument is come like 1 over something. So the large asymptotic of Levy stable distribution gives the small behavior of this one. On the other hand, small argument properties of Levy stable distribution give the large behavior of this one. So therefore, if the Levy stable distribution, the mean may not exist or the variance may not exist, but here the mean and variance exist actually. So this is a well-defined thing which mean and variance exist. Okay, because this large behavior comes from the small argument behavior of the Levy stable distribution. Okay, so you can, so as I had said before, you cannot always write down the Levy stable distribution explicitly. You can only express in terms of a Laplace transform, but there are some particular cases where you can do. For example, alpha equal to half. What is the answer? You know the answer for alpha equal to half. What is the answer for alpha equal to half? Alpha equal to 1, sorry. Alpha equal to 1. Alpha equal to 1 is the mean axis. What is the answer? So it's the same as this random walk case. Huh?
That's the function before. It's also called the Mittag-Leffler.
This is not the Mittag-Leffler distribution. I think Mittag-Leffler distribution is this your generalized exponential, right? Which is basically, see exponential if you write it's, okay. Exponential if you write it's sum over x to the power n by gamma of 1 plus n. And this is your exponential, right? I think this Mittag-Leffler, whatever, this one is of x. I think it's defined like that, n equal to 0 to infinity, x to the power n by gamma of 1 plus alpha n or something like that. I think this is what this Mittag-Leffler function. Okay, fine. Yeah, okay. Okay, so there might be some relation, yeah, between that. Okay, so this is what you have. So let me just, okay, so you can write down the how small x behavior, large x behavior, everything, and in particular for large, you can also write down for another 1 or 2 other values of alpha. Let me not just tell you, let me just only tell you the large x behavior with some prefactors. So it goes like square root of 2 minus alpha pi alpha x by 2 to the power minus 1 minus alpha by 2 minus alpha, and then where is this guy? Yeah, exponential of minus 2 by alpha minus 1 alpha x by 2, 2 by 2 minus alpha. Again, you see that when you put alpha equal to 1, actually you just get that same tail, okay? So this is what you have. You can also find out the mean records by knowing the negative moments of this. So as I said that the moments of this guy may not exist, higher moments, but the negative moments exist. Negative mean negative powers of x exist. So knowing that, you can also write down this thing. In particular, mean is given by this one, gamma of 1 plus alpha by 2. Okay, you can also find out how the variance behave and other things basically. Okay, so you see that this basically, so alpha equal to 2, alpha equal to 1 case is like the random one, but it basically generalized to any alpha between 0 and 1. Yeah. So alpha is between 0 and 1. Yeah. Okay. So you can also do other things, but okay, let me just not this thing. So okay, during this course, basically what I have tried to do, I have just tried to give an introduction to this extreme value statistics and record statistics, and I have stick to very basic things. So I thought that I'll just give you the introductory thing, and then once you have that, you can go ahead and read other papers. Record statistics also, of course, there are a lot of recent works. For example, Satya has done a lot of works. This Joachim Krug has done a lot of work on record statistics, and you can ask various questions now. See, these are the simplest questions, this thing on which you can build it up, and there are various, and you just go ahead and read all those papers. So I have given some references again. I have only given a few references based on which, let's say, I have prepared my talk. Intentionally, I didn't put a lot of references because I thought that if I give you a lot of references, you are not going to look at any of them, right? So I've just given very few of them, and okay, thank you very much.